El tipo de mujer siempre es
Bueno, ¿qué tal? Buenos días a todos. Bienvenidos a la Agencia Espacial Mexicana. Nos es muy grato que nos estén aquí acompañando y pues les pido por favor que den una cordial bienvenida al doctor Mengucho, que viene de un lugar bastante lejano, viene de QTech, de Japón, y también acompañándolos su estudiante de doctorado, Rodrigo. Entonces, por favor, denle un cordial aplauso. Muchas gracias. Y pues encargado de generar todo este tipo de eventos, mi jefe, el maestro Carlos Duarte, que está aquí a nuestras espaldas, también les pido por favor un cordial aplauso. Muchas gracias. Pues iniciamos. Olvidé decir mi nombre, es Blanca Rebollar Trejo, directora de formación de Capital Humano especializado en el campo espacial. Y pues muchas gracias, espero que disfruten mucho esta plática y que les sea provechosa para su carrera profesional. Con permiso.
Okay. Good morning.
Good morning.
My name is Mencho. I came from the Kyushu Institute of Technologies. Today, thank you very much for giving me this opportunity. For yesterday, I went to the IPNs in the mornings and UNAMs in the afternoons, and I gave a seminar about my my schools and how we do research and education of space technologies. So today, I'd like to show to these AM people about the similar things. So can you? So I have presentations. So about a little bit more than 1 hour. Okay. So after this, you can ask me any questions. And also the Rodrigo, he's a student from IPNs studying at my places. So if you want to know about the detail of life in Japan, you can ask him in Spanish. Okay, so the title is How to Start Satellite Programs, and what has one? So introductions to space engineering research and. So first, let me introduce QTech. Kyushu Institute of Technologies. Because it is long, in short, we call QTech. It was founded in 1909. It's in here. From Tokyo, it's about 1,000 kilometers and almost close to the police. And Japan is made of 4 islands: Hokkaido, Honshu, Shikoku, and Kyushu. And Kita means north. So it says that the north of Kyushu. So close to Kyushu. And we are national universities, founded in 1909, for a little over 100 years. And 6,000 students and about 400 staff. And we are located in these regions. This is the date of 100 years. Other than this, all of the buildings are new, but this is only the new. So, city of Kitakyushu, yes, we are facing the sea, so we have a lot of the nice seafood. Yes. Okay, we have this Japanese traditional castles, and this is a very beautiful wisteria gardens. This was listed #1 in the top 31 beautiful places in Japan by CNN. So if you come in from the end of April to beginning of May, it's very, very beautiful. Right now, there's nothing. Even if you come now, that's it. So, space engineering educations at the QTech. I came to this university in 1996. So even before I came, there is some educational courses focusing to undergraduate and graduate. So this is these courses are given in Japanese. And however, we are going to start a Department of Space Systems Engineering from 2018. This is dedicated to the space systems. This course is a part of mechanical engineering, but this one we are going to make some dedicated department and starting 2018. So no aircraft, just a space. And we are also the member of IAF. We are the only university member from Japan. So that's the reason why I came to Mexico this time to attend IAC last week and I'm here this week. So let me introduce LACEN. LACEN, Laboratory of Spacecraft Environment Interaction Engineering. This is a laboratory I have been serving as a director since 2004. This LACEN, if you know French, it's a river in Paris. And so the names I took because every river starts from a very single tiny drop of water, and gradually grows and goes to the ocean. So we started very small, about 6 or 7 members, and so we thought eventually we wanted to become big, or like a river, but we are still small. So eventually we hope will become as big as LACEN. And the annual budget is about 1 to 2 million US dollars. So we do space environment. So the main theme is how to survive in space. Because as you know, space, no Earth, so the thermal control is difficult, and surrounded by conductive plasmas. So it's very easy to discharge when we have high voltage. That's my main theme. And strong radiations. And so not only human beings, also semiconductors and materials degrade quickly or malfunction. And hypervelocities, we have a small particles flying at about 10 kilometers per second. So 1 centimeter particles, if it hits, it's just catastrophic. Moreover, we cannot repair. Okay. Space is different from automobiles or airplanes. Airplanes go to routine maintenance every 6 months or 1 year. Automobiles, you go to gas stations, and you go to the factories. I don't know in Mexico every year or 2 years. so some people do. So they are designed so that it designed in a way that they can be repaired. But space, except ISS and the Hubble Space Telescope, it's not designed that way. So we have to make sure it works maintenance-free for very long times, longer than 10 years. The longest space systems, longest surviving space system is the Voyager 1 and Voyager 2, which was launched 1976 or something. So it's almost 40 years. So it's really amazing. 40 years. So it's completely different from other areas of the engineering. So space, we have to make sure everything's before the launch. So our mission is to serve humanity's difficulty, the development of space activities, research and development of space environment technology. So how to survive, make sure the space system survives in space. So the research area, we do the 4 areas. One is electrostatic discharges, one is orbital debris, one is material degradations, and one is non-satellite environment. So it's kind of unique. We don't do the something like we don't do much something like the propulsions or attitude controls. Although we do some, because he's doing attitude controls. Although we do some, but mainly we do this. The things other people don't do. Because space environment, every organization, when they build a space systems, they need at least 1 or 2 experts about how the systems interact with the environment and how to mitigate if the effect is not good. And they don't need hundreds of engineers, such engineers, but they need at least one or two. So what I tell my students is that if you become such a one or two and get a job or in agencies or in a company, you'll never lose a job because nobody can replace. So that's what he's hoping. So for electrostatic discharges, it's caused by spacecraft chargings, and this is could you click video? Sorry. Yes, we have something like this lightning on the surface. If the surface is charged and exceeds certain voltage. So this is sometimes very fatal to spacecraft operations. If this discharge occurs at the wrong point, at the wrong times, we may lose the entire satellite. That happened at the end of 90s to the beginning of 2000. Many commercial satellites failed because of distance, and one commercial satellite cost us $300 or $400 million, and huge financial damages. So we are asked to do the testings, and we have this very special, unique testing facilities. Not many countries have these testing facilities. They exist only in the US, also France, and in Japan. We are capable of testing for different environments, geosynchronous and polar Earth orbit and low Earth orbit. And using these facilities, we have tested all of these, most of the Japanese satellites since 2000. And also we're testing the Indians and the Americans and the Chinese satellites. These are the satellites of very expensive and where the reliability is really the top priorities. And so this is completely different world from a small satellite. When I ask the money to do the testings, they gave me the money. So it's a very good time. So we have tested these ones. And based on that experience, I was the project lead of this ISO standardizations, and so we published this solar panel ESP ground test. It's called ISO 1131. And it was an international project, US, Europe, China, and India. So we have been working on international project since then, and many partners. So one example is that we did experiment on onboard ISS. We tested these solar cells to the space environment, and we put this the electronics. This is the COTS-based electronics. This was designed by us, and so we flew this one. And this is a joint experiment with Lockheed Martin's and a number of research laboratories and JAXA. So these are American astronauts. And we did experiment on board the US modules, not the Japanese one. And this came back to the Earth. Dragon capsule brought this back. And we opened this once, and it was surprisingly looked new. It was exposed 2 years to the radiations, but I expected these cables become very dark and very, very fragile. But yes, it looked like this. This is before the launch. But this after coming back from space, it looked really like this. So it's now sitting in the exhibition place of my laboratory. For another experiment, we did this the charging experiment. This is Japanese cargo vehicles. This is ISS. We put a charging sensors. This was joint research with JAXA. And concern was that these vehicles may have different potentials with ISS. Then during the docking, if the potential difference is 100 or 200 volt, we may have a spark discharge between. Then that current may damage electronics in ISS. So that was the concern. So we try to measure the potentials of difference. And so we put a charging sensor here. And this charging sensor was developed based on a charging sensor of copy machine. Copy machines use a toner. A toner is charged. Right? That's why you smell the ozone. And so toner machines carry these charging sensors. So we converted that one to the space for the charging sensor of the space. It wasn't so difficult. So we finished developing in 1 year. So quickly we did it, we modified and put that on board and the code. The total program cost for us, for QTech, total program cost was I think less than $10,000. It was for easy and for inexpensive space experiment. So we had this the Space Development Utilization Award by Ministry of Economic Trade Industries. Another research area, hypervelocity test facilities. These guns, these are different guns. They are two-stage light gas guns. It uses black powder here and use the heliums here. And so compress the heliums and accelerate. So this can generate these particles speed of 6.2 kilometers per second. And we have several of these guns. Also, material degradations. Spacecraft surface materials, especially the polymer, it is a key for the thermal control. So nowadays, many polymers used. One very famous one is Kapton. And those polymers degrade due to UV, or in lower orbit, oxygens exist in the form of atoms. So they are very chemically active. Also, radiations. So we have to investigate how those polymers degrade. Also, we are also investigating degradation of a carbon fiber. Because nowadays, many the space structures made of carbon. And especially if you think of the larger telescope or large antenna in space, it's made by carbon fiber. And so that may, over the time, long times, that may change the mechanical property. Then the shape may change. And so, but that antennas or the telescope has to maintain its shape for long times. So that's really the issue now. And nanosatellite testings, we have these facilities capable of doing all of the tests for satellite up to 50 centimeters, 50 kilograms. This limit came from the JAXA requirement on H2A piggyback. On JAXA, when they launch small satellite on the piggy, the requirement is less than 50 centimeters, 50 kilo. So that's the definition of nanosatellite in Japan. So we have these facilities, and using these facilities, we opened a Center for Nanosatellite Testing. This was established in 2010, and with the government fundings. This is basically one-stop solutions of the satellite, small satellite developers. Because these satellites, especially this one, very small. Right? So if we want to test using a JAXA facilities, their facilities are too big. This is 1.5 meters, but in terms of JAXA standard, this is still too small. So if we go to JAXA, their chamber is 10 meters or something. So you can put a bus inside. And so we cannot ask to put this in the channel. This may be lost inside channel. so these are so small, and so satellite developers, mainly universities and small companies, they are looking for places to test. And because this kind of facility is very special, so we cannot find. This one maybe, this vibration machine maybe, but this thermal vacuum is very difficult to find. So we asked the government, and the government invested about $2 million to have this kind of facilities. And we are now testing from the Japanese universities, also Japanese company, also the foreign entities. So right now in Japan, more than 20 universities and also 3 private companies build a small satellite. So this is a satellite we tested. So this counts about 2/3 of a less than 50 kilo Japanese satellite, and more than 30. And also we tested, this is Singapore, and this is Philippines, and also we test satellite from Malaysia and South Korea. And because CubeSat, this kind of CubeSat, they can hand carry by airplane. They can put in a cabin. Right? And so it's very easy to bring that to Japan for the testing. So we are also working on international standard called Space Systems Design Qualifications and Acceptance Test of Small Spacecraft and Unit. So basically this is small satellite testing. And we are also working on requirement for small spacecraft. So we have this types of the workshops once every year. Next one is in January in Tokyo. We talk mostly about many standard issues, not only testings, but the various standard issues like interface and communications and test and protocols. Those. Yes. This one is very important if you are younger than 35. This is the fellowship programs. This is United Nations Japan long-term fellowship programs. This one provides fellowships to students from non-spacefaring countries. Mexico is one of them. And provides tuition and living costs and on-the-job training from satellite development, especially infrastructure, because we have we can teach about the testing and how to build testing facilities. It's called a postgraduate study on non-satellite technologies. It's called PNST. 6 students, 2 masters, and 4 doctors. And it's funded by Japanese government fellowships. And if you are interested, just Google PNST UNSA. And everything is electronic, so you can find all the materials. And application for October admission is now open. Deadline is January 22nd, 2017. So make sure that if you want to have it. So for the selection criteria, we want the students who have the passions to be engaged in space technologies. So we judge this one from the essays and also by the Skype interview. And applicant must have also the good English skills. Also must be under age 35. So this year, from this October, we have one of your staff under this policy. So you can either ask him or you can ask. And to accommodate those students from abroad, we started this new courses, Space Engineering International course. This is an English course. Everything is given in English. And we have a research toward the master or doctor degrees and on-the-job training such as the space environment testing workshop. and project-based learning through a space project like this one, or the student participate in missions definitions, mission designs, and they participate in a UNICEF mission idea contest. And lectures are given in English. This is the student compositions. You see, many from Africa, many from Southeast Asia, many from Latin America. We have no students from China or India, from Russia or US or Canada. Very few from the Europe. Because we target students from non-spacefaring countries. We try to help those countries by teaching the students. And right now we have the 34 foreign students from 19 countries. This 20 also includes Japan. And actually Mexico, from this October, it's a kind of becoming the big population, 3 students. Another country who had 3, the Mongolians and Bangladesh and Ghana. So yeah, it's quite big. And you see, lots of the Latin American countries. So we have quite a few Spanish-speaking populations. In one sense, it's not good because they are supposed to speak either Japanese or English. No Spanish, but they have we have lots of Spanish speaking. And alumni, we already have some alumni. They went back to the agencies, UNSC, Thailand, Sudan, and Nikon, and also he just graduated and going back to the Egypt now. We have also students from NASA of Nigeria. So I'll explain about our satellite project. So we have so far launched 3 satellites. This is not a satellite. This is the spacecraft went to the asteroid. So it's not a satellite. So this is the first satellite we launched 2012, and this is the second one, and this is third one. So actually we are launching every 2 years. And 41, this is the first satellite, CubeSat. We tried to launch from India, but contract didn't go well, so we put this in storage. These are all, these 3 were all launched by H2A, and it was free launch. Yes, JAXA gave us a free launch, so it was very nice. And this Alba Perex 3, this is jointly with Singapore, and this is a pulse plasma thrusters. This is the birth constellations. This I'll explain later. This is constellation of 4 satellites. And this is another joint project with the Singapore. That's what Rodrigo is working on. So these are the satellite projects. So today I'm going to talk about this one, and this one, and this one. So nano-satellite missions. Non-satellite missions, we can divide into 3 types. One, education. We learn systems engineering, students learn systems engineering through satellite development. 2 is technology demonstration and science. So on-orbit demonstrations of new technologies, or make our own satellites to the experiment if we want to do something in space. Or practical application. This is to build a satellite for others by receiving money. So for other universities, because we don't do business, it's limited to this one. But I really think time has changed. When I was a student, no way to think about building satellite by ourselves and to do the experiment by ourselves. So what I did when I was a student. We did a very basic research and did experiment, but we never know when it becomes a reality. So my my area was, when I was undergraduate, I did an experiment on ion thrusters. That time still ion thruster is nobody was going to become reality. But right now, if the student want to do experiment in space, they can build a satellite and launch it. So that's really different. So really the time has changed. So it's very, I think present situation is very good for the education and research, especially for universities. For Hori 2 missions, this first satellite was education and technology demonstration. So satellite and systems engineering. So we teach systems engineering by a satellite building. So I think we are not teaching really space technologies to students, but we are teaching systems engineering to the students. So even if they cannot get the jobs in the space sector after they graduate, because Japanese space sector is small, not everybody can get a job in the space. But it's okay. For me, it's okay because they have enough skills of systems engineering, so they can work in an industry such as automobiles, aircraft, railroad, or the plant, or the electronics. Those requires these disciplines of systems engineering. So they can work in any industry. And the satellite is really the good tools to teach systems engineering because it involves very broad disciplines: systems engineering, project management, electronics, mechanical engineering, material sciences, and everything. And numerous number of parts. This, I think it says 10,000 parts here. So it's a very good tool. So we are teaching systems engineering using the satellite as a tool. That's why we are going to start a new department of space systems engineering. So the motto is we teach systems engineering using space as a tool. For Hori 4, it's called, another name is Aegis, Earth Event Generators and Investigation Satellite. Its mission statement is to acquire on-orbit data of discharge phenomena occurring on high voltage solar array. So we are trying to take an image like the one I showed you before. So the lightning like the images of some discharge flashes. Also, we try to capture current waveforms of discharge by oscilloscope. Surprisingly, no satellite ever carried oscilloscope because people are not interested in a fast transient phenomenon. So we developed oscilloscope by ourselves and put in a satellite and connected camera to the oscilloscope, and so that this can be activated by the oscilloscope. Another aspect of Hori 4 is this team. It's quite diverse. 18 countries. If you go to ESA member country, I think more than 20. I'm sure, but it's very common to see these countries involved in missions. But in a university project, it's very rare to find this kind of diversity. Right. And so in these pictures, only 5 or 6 Japanese in here, all other foreign. So it's quite challenging, but we finally made it. For Hori 2 and Hori 4, Hori 2 was really the first satellite we developed. Prime mission was education. So because it was education, students did everything. Yes, we outsourced some the difficult part, such as the solar panels or the communication radios, but most of things are designed and built by students. And they are mostly Japanese, and 10 students. And the total budget was $200,000. This doesn't count the launch. And this 200,000, so it's surprisingly affordable. And university paid all of this. So I asked the university president that, to support this one. because this was the first satellite of the university. That time, several Japanese universities already launched a satellite. So university satellite wasn't new, but still it was the first satellite of our universities. Also, 2010, this time it's around 100th anniversary of the school. So I thought that the good to persuade the alumni association. So we approached alumni association and asked for the support. Folio 4, on the other hand, total budget was about 1.5 million US dollars. Based on the success of Folio 2, I submitted research grant applications, and I got the funding from Japanese Society of Promotion Sciences. This is equivalent to the Konofito. And so, with this money, it's very difficult to fail. These ones, I can still fail. Because the stakeholders just universities. And the missions in the education. So once the students build a satellite and deliver the satellite to JAXA, the minimum success is obtained. Even if it is dead in space, it's still okay. However, this one, unless we get the data from the orbit, it's a failure. So we can say I can say sorry by using this model. So it's very difficult this time. So for Folio 4, this is development philosophy. We learned many lessons from Folio 2, mainly two. If we summarize, if we prioritize these two lessons, we had a very severe accident due to single event nature. This is radiation phenomena. We knew this is important, of course. So we put some shielding, and so also we put some overcurrent protections, and also circuit breakers. But we didn't verify. We thought maybe this will work. But in the world of the space, there's no word of maybe. We really need to verify. Unless we verify, yes, no maybe. So we suffered very serious malfunctions, and so also anything can happen in space. Satellite was perfect for the first 3 weeks. It was really perfect, and because this was the first satellite, we are very happy, and every day we are just checking the battery voltage and temperature, and being amazed. And we are talking about when we started the first experiment, and so we said maybe next week, and so also I went to the conference in Slovakia. They are having a 4S symposium. The very nice places, Slovakia, in the beach. And I was thinking to have some 1 week vacations. And after that, I was planning to do an experiment. But when I went to the Slovakia, I got an email from student that the satellite lost the communication. so it occurred 3 weeks after. So fortunately, it recovered after 1 month. So it took 1 month to recover, but it recovered. So we could do the main mission. It was okay. But the lessons is anything can happen in space, especially small satellite. Because it's not the testings and verification on the ground is not really the thorough enough. It's not 100%. So there are some things we may have overlooked. So that's the thing we overlooked in single event nature. But anything can happen. So the lesson is achieve the minimum success as soon as possible after the launch. So that's the lesson. So we try to minimize possibilities of anomaly of the satellite bus. So try to minimize single point of failure and prevent the loss of communications. If we lose the communications, that's really serious. And also, it's very bad for your psychological health. So you cannot sleep. Right? So we test against SDLs and try to achieve minimum success, and no matter what happens to the satellite. So we put several redundancy for this main mission experiment. And the setup operational plan of the first 1 week from launch, the plan should include the main mission experiment. And so we did lots of the simulations of our first 1 week, and using the real satellite and ground station. So we just concentrated on that one. And outsource tasks if necessary, and try not to do everything in-house. And to have more reliability, and also to save the time. So we launched. Could you click on this? This was the sound. So this is a very beautiful evening launch. It's located in Southern Islands. I wish I could be there, but because I have to stay in the ground session, I couldn't. So I sent one student. He was very happy. So after the launch, yes, could you please? After the launch, separations. We can watch the videos of satellite separations from rocket. So we can make sure the satellite was released. And also we can check the initial rotation. This is a very important information because that affects the communications of the satellite. So satellite was launched, and about 1 hour later, this was over the Argentina. And so 1 hour later, satellite came over the Japan. So we are waiting for the first contact. And the press was there, and all the newspaper people asked me that how do I feel that time. I said that it's just rocket. I didn't do anything on this rocket, and so they just did. Rocket people did their jobs. I haven't done any job yet. So we are waiting until we hear the first sound from the satellite. I cannot say we succeeded. So we are waiting for the first sound from the satellite. Would you click video?
The prediction was successful! The prediction was successful!
That is a good moment. This is really addictive. You want to do it again. So it's very good to hear the first one. So we did this experiment. This is a discharge experiment. So we have a camera. We try to capture the discharge on these solar panels, and using an oscilloscope. So we succeeded. Yes. 1 week. 1 week after the launch, we did the simulations. We activated the experiment, and we captured the image of this in here. And also, we observed discharge current waveforms. So this is the first time in the world. Even the NASA or even the JAXA or ESA, they never did this one. This is the first time we observed real discharge waveforms and also the discharge images. So before then, people were very skeptical when we say the discharges in space. Like, have you ever confirmed that one? Somebody even said the discharge in space like a black magic. So we are very happy to demonstrate this. So we did several the outreach missions. This is we have some very small cameras, very old. I think the camera is used for the mobile phones about 5 or 6 years ago. So it's very tiny, but we could capture the Nile River. Here is the cartoons, and she's a student from Sudan. She was in charge of the camera. So she's very happy. She already graduated, went home. She's working at the Sudan Space Agency, but she's so happy to see her homeland. So another thing, outreach event. This is quite unique and also very powerful outreach thing. We carry music synthesizer, so satellite can sing. And so the Yagi antennas, even elementary school children can build this one. And we connect to the UHF transceiver. This we need to buy, but about $100. So we do the outreach event for the children over the roof, and they chase the satellite in the sky. And once they succeed, they can hear the music. And if we do that in the night, we give the children the star chart. And so the children look at those star charts and look at those constellations and to follow those satellites. So they can really realize satellite is moving in the sky. And in Hollywood too, we did this event using Morse signals. But Morse signals is kind of boring, so because children can't understand. But this one, yes, they can really understand. So could you click video? Yes, that's a very traditional Japanese. Of course, it's a copyright free. so the satellite can sing, right? And so perhaps the next time we put a reaction code on the satellite, and for while the satellite sings, we move the reaction code, so the satellite also can dance. Yeah, singing and also dancing. So now the BIRDS project. This one is a constellations of 4 1U CubeSats owned by Bangladesh, Ghana, Japan, and Mongolia. And these Bangladesh, Ghana, Mongolia, these are the first satellite for the country. They've never owned the satellite. They didn't even buy the satellite from other foreign countries. So this is really the first one. And so mission is a successfully build and operate the first satellite of the nation, and make the first step toward indigenous and sustainable space programs. So satellites are made by students at QTech. So they are students sent from each country and studying at the Space Engineering International course. And this will be released from ISS in 2017. Yes, we already secured launch. And we now have 5 megapixel camera. So we try to take a picture of the Earth and about 100 meter resolution. And also we have a serious science experiment. So this BIRDS project we operate by network. QTech, Mongolia, Bangladesh, Ghana, we have ground stations. Also, Taiwan, Thailand, Nigeria, they also joined ground station network. For using 7 ground stations operating 4 satellites, and we can overcome some difficulty of the CubeSat. One difficulty is the communication speed. This CubeSat carries a 9.6 kbps radio, but it's still not enough to download the much data. But by having several ground stations, we can increase the communication times. So we can increase 3 or 4 times of the communication speed by doing it. So students working together, and sometimes they have having fun, and sometimes they're having hard times. And, so I put everybody in one group. Team is made of 15 students, and I put everybody in one room and tell them to communicate constantly and try not to use emails, because you know if you write emails, you have to wait for the reply to come. Right? If you wait for half days, that half day is lost. Right? And so that's really the way. So I tell the student, if you are communicating just to one person, then just stand up and call. So, but they don't do. Those young people, they always rely on texting. But yes, we try to do that. Minimize the waste. So in this project, we are experiment one way of the lean satellite concept. So by minimizing waste, so everybody staying in one room, and now they move to the another buildings, and in that buildings, next to their office, we have a clean room, and downstairs they have all the testing facilities, and the next buildings we have a ground stations. So everything is finished within a 30-meter radius. So there are no loss of the transportations, no loss of the communication. So it's really the experiment. So educational aspect of this project is that the short-term goal is build and operate satellites. So give the students confidence that they can do it. It's very important. When we build our own first satellite, I could tell the students that because other universities already built and launched satellite, why do we think we cannot do that? And so they can think they can do. So if we demonstrate to students from the Ghana, Mongolia, and Bangladesh that they can build a satellite, it has a tremendous effect on those young people in those countries, that they can build satellite. So that's the short-term goals. And long-term goals is we let the students go back to their own countries and start their own programs. And we already have an agreement with the home universities. They are sent by the universities. And so we have agreement that they are starting space research laboratories. And they hire those students as a staff of the launching staff of the laboratories. So once they return, they start a second satellite. For the full mission success, is the former students successfully build and operate second satellite in their home countries. Then this project is a success. And during this process, we let the student learn entire process of satellite program from beginning to end. This is important to know from a real mission concept to the disposals. Then they know when they have to do what, and how they decide, and what is most important in each process. So they witness each decision process and make decisions by themselves. Another important thing is to fit the project within degree timelines, the 2 years for the master. It's quite challenging to fit everything 2 years, including operations up to disposal. But this is now possible using these ISS launch systems of CubeSat. And because we can predict, also we can control the launch. And 2 years we can fit that one. And capacity building aspect, so we target university space programs, not the agency this time. Because we often see national space programs suffer disruptions because of political and economical disturbance. I'm talking about the AMs, but I'm talking about other companies. I often see some countries, 1 year they launch satellite and celebrate nationwide, and next year no budget, and the year after also no budget, and the year after they get big fundings and try to buy another satellite. That happens. But if that happens, the problem is those people will leave the agency. And so after the spending so much, investing so much on the human resources, and however, during those hard times, they leave, and the country lose the talent. So that's a problem. So university space programs is a real kind of immune to such a disturbance. As long as professor stays, as long as professor keeps laboratories and students enter, they can, although it is low profiles, they can maintain. And when the good time comes, they can also prevail. So, however, at the same time, university space programs cannot grow forever. They need to hand over to the national space programs. But to start with minimum budget, university is a really ideal places. So that's why we chose CubeSat as a training platform, because this is affordable enough at the university budget level. Like I said, we started the new first ones, $200,000. So yeah, it's quite affordable. And even after handing over the big project to outside body, like the agencies or private companies, university still can continue its own space researches and education. This education is very important. And BARS project also has aspect of cross-border networks. We try to provide, create 2 networks, human networks and ground station networks. Those students who stay together nearly 20 hours a day. They create very, very huge, strong bonds. And ground station networks is really the backbones of inter-university networks. So it enables this constellation operation in the future. So after all, these networks will assist infant space programs to survive the hard times initially. So other international project we do, we work with Singapore, already 3 projects. Yeah. And also Costa Rica, I think that you know this well. And so when student comes, they have opportunities to join this international satellite project as a QTEX student, even if we don't have even if that country doesn't have the BARS project. So finally, how to start the space programs. I'm not sure it's appropriate to tell the AEM people because you already started. So this is my idea. This is my idea. It may be different from what you think. But the national space programs, to me, it has to serve the needs of country. First, by identifying the needs and proposing space-based solutions, and devising strategic plans, and make the policy to implement the plans and carry out the plans. And development phase, several generations. First generations may be buying satellite from spacefaring countries. Second generations design satellite in home countries and to build it in foreign countries. And third generations design and build satellite in home countries. And perhaps in somewhere around here, the need of space agencies to be responsible for policy planning and implementation. Because this stage requires lots of the investment. And perhaps only the government can provide. And in this stage, developing human resources to form the first core of the space agency is really critical. And also sustainability is really the key. And because enough and continuous development of human resources, I think in Mexico you have already several universities working on a curriculum, so it's good. And persistent research and study in this field. And prepare professionals and start to do some research on modern satellite technologies. So for this ones, universities or research institutions are responsible for these tasks. In many countries, it doesn't go well this way. And they choose different paths. One success example is perhaps the UAE. UAE first they collaborated with South Korea, and they bought a satellite, and they built their designs in the UAE, and they built a second satellite in Korea, and third they developed everything. Now they are going to the Mars, and also they are building university curriculums in several universities now, in Dubai and also Abu Dhabi. So it's kind of success stories. I can tell many bad stories, but I shouldn't tell you. So importance of university space programs. This the role is to research, education, and service to society. Yes, human resource supplies and research, and fundamental research and industry promotion and outreach. Actually, Japanese space program started from the University of Tokyo. He's a Professor Itokawa. He's the founder of Japanese space program. He's not only professor, he's also the project manager, also system engineer. So he's really the leader. And started from University of Tokyo, and it eventually became the national space program, such as JAXA. So, national space programs and university space programs, they are complementary each other. University space programs provide the human resources, also the cutting-edge research result to the national space programs. National space programs make policies and perhaps provide money to the and domestic industries. And yes, so society is really the stakeholder. And so they have to explain what they are doing to the society. Also, have to respond to the needs of the society. And young people enter the university space programs because they don't go to the national space program directly. They go, and also foreign countries. This kind of relationship. So strategy. This is for the university satellite. Strategy for the first satellite. It's better to avoid trying to do everything with the first satellite. Research or education or the outreach or industry promotions. You may want to do everything, but it's very difficult and you lose the focus. And here is the Japanese saying, those who chase two rabbits catch neither. Right? Often people try to catch 3 or 4 rabbits, but they end up catching none of them. Yeah. So first satellite maybe to put the emphasis on learning process of entire process of satellite program, from mission definition to disposals, and get the confidence and understand what are really important. It's not really technologies. Importance is a systems engineering, project management, teamwork, and strong will. These are the important. The making buildings, the component is not really important for the first ones at least. So for this one, 1 UCubeSat is good enough for the first satellite. When I talk to the other companies, often they say, no, 1 UCubeSat it's nothing, and we cannot explain, and so we want to take a pictures, and they say many things. But I always say, this is the first one. Just finish the first one as quickly as possible, and move to the second one. For concentrate on mission payload, Other can be cost components purchased from the market. At least you need to develop mission payload because this is unique. For the second satellite, we incorporate lessons learned from the first satellite because this is a risk management. Risk management is especially important in a small satellite because small satellite is full of risk because we are using non-space grade parts, non-grade space technologies. We outsource to manufacturer who is not familiar with space. Okay, so there are many also people are not experienced. So there are many risks. So we have to evaluate, identify, evaluate, and mitigate the risks. And but risk mitigation takes money and time. And more tests is necessary, and we may need to buy high-grade parts. But we cannot do everything. There are many risks. We cannot do risk mitigation for all of the risks. So we have to select. We have to prioritize what risk is most important, what risk is most critical. So this assessing is really the key. And it must be based on experience of the personnel working on. So needs to accumulate experience as fast as possible. So that's why losing the talent is really the bad things to the space programs. You really need to maintain those the experience in a human being. And we can utilize short life cycles of small satellites. Life cycle of some industrial products, mobile phones once every 1 to 2 years, automobile 4 to 6 years, traditional satellite 6 to 10 years, small satellites half to 2 years. So we are fortunate that small satellite we can build many satellites in a short time. Traditional satellite, often in JAXA, one satellite program takes even 10 years. So engineers who enter JAXA until the end of his career, it may be lucky if he can participate in a 3 satellites project. So in that case, accumulating experience in human beings is impossible. That's why they rely on a document, for heavy documents. But for small satellite, these guys can experience 6 or nearly 10 satellites maybe in 5 or 6 years. So can experience many areas. So then maybe after 5 or 6 years, this person can judge what is most important. And he can say, okay, this risk can be left aside at this moment. We should work on this one. And second, we should do this. So this planning can be done. So risk management and continuities. Start while first satellite project is still running because we can utilize those personnel working on first satellite. Avoid gap in experience and know-how. And it's better to base on a successful or failure of first satellite. Try to avoid radical change from first satellite. And we can start in a first in-house development of some components, but keep reliable components from first satellite for the critical subsystems, such as computers, communications, and electrical power systems. And gradually you can replace it. And also gradually shift toward research emphasis to generate scientific papers, especially in the universities. So the third satellite or radars. For the university space programs, it's a time to make a strategic decisions or make a strategy. And university satellite cannot grow forever. So big satellite project to be done by national space programs. And satellite for the practical use may be done by private companies. And based on strategic decisions on future directions, university can go to education, or university can go to research, or can go to the practical use. But it may be up to the proof of concept, because for the business phases, it should be done by private company. or the university should make a private company. So in Japan, big satellite for civil and military use is done by JAXA. Commercial satellite is done by private companies. And science satellites done by Institute of Space and Astronautical Science. This is now part of JAXA, but originally this is University of Tokyo. And experiment education satellites, the small satellite by many other universities. So this load sharing is done, and it's done by defined by the strategies of a space program. So last two slides. So what we can do for you, and test your satellites. We did testing for Singapore, Philippines, Vietnam, Malaysia, and testing for components from Finland and Egypt. And we can train engineer students on satellite testing using short course. We did for South Korea and Philippines. And educate engineer students on space engineering through the Space Engineering International course. So we do various countries, now more than 20 countries. The assist satellite programs using JAXA ISS launch. And it's extremely affordable. One UCubeSat costs only $30,000. If you ask the other providers, it's about 3 times. And ISS launch is also very good because it is predictable, because it is done by the cargo, satellite is carried by cargo vehicles. There are 3 or 4 cargo launches every year, either by Japan or by US. So JAXA put the satellite, if they don't have a JAXA launchers, they put in either Dragons or orbital Atlas. So they can promise if we say we want to launch first half of 2018, they can do that. Actually, Philippines, they are more specific. They wanted to launch before the presidential election. It was April, right? And satellite was launched. I think satellite was released 2 or 3 weeks before the elections, right? And so they tried to help the one particular candidate, but you know the result, right? Now we have very unique Filipino president. So it didn't work. But anyway, it can be controlled. And of course, currently JAXA regulation says you cannot directly go to JAXA. You need to team up with a Japanese entity. So that's why we are helping Costa Rica. And we are representing Costa Rica to the JAXA. And there are other also private company who does for the business. Because we are university, we don't do this for business. We do only when the country sends the students. Because those students will work on this project. And so consulting, testing, and launch coordination for Costa Rica and Turkey. And we can start up CubeSat programs by SBIC students. We are now working on Bangladesh, Mongolia, Ghana for BUZZ 1. For BUZZ 2, we work with Bhutan and Philippines and also Malaysia. Bhutan is a very unique case, very interesting. Bhutan is located just north of India. Population is 870,000, less than 1 million. It's a tiny part of Mexico City. So even for such a small country, they are interested in our space. So the final was, yes, we are ready to assist the Mexican space programs, other friends. And also, we accept talented Mexican students to Space Engineering International course by either by UN Japan Fellowship programs. So remember, application deadline is January 22nd. And or by support of Mexican government, to be specific, CONFITO, or individual universities, or self-funded. One student is staying in schools at self-funded from Mexico. So what you need is strong wills to contribute to Mexican space histories. And I tell those students from Bangladesh, Mongolia, and Ghana. I tell these guys, they are from the Mongolia, Ghana, and Bangladesh. What you are doing is the things to be written in a history book of your country, like first satellite of the country. And maybe you'll appear in a textbook of science. Okay. So maybe 20 years later, if you want to tell your kids that you did the first satellite, and my face is on your textbook. And so if you want to say that to your kids, take their nice picture, so that this will appear in a textbook of your country. So so if you want to put your face in a textbook, please. Okay, that's it. Thank you very much.
Profesor Cho, por this wonderful lecture. Y ahora pues vamos a hacer algunas preguntas, comentarios. Si las quieren hacer en español, mucho gusto las traduciré. Un comentario. Comments.
Yeah, I have a question. Do you are doing the control of the satellites with the FPGAs or what type of control?
No, we don't use FPGA, not yet. We are using some microprocessors, which is used for automobile. So we are still primitive.
But you have you want to do it in the future? Or?
Yes, FPGA makes things very the simplest. The only issue is the power. So as long as we stay in the CubeSat, unless we have the FPGA which requires which does not require much power, it's very difficult. Right now, FPGA consumes too much power.
Otra pregunta.
I have another question. What did you recommend for to use the composite materials, or do you prefer for the metal alloys, or do you prefer another material?
This one is made of composite. Actually, these are the metals. This one was made of composite because a professor who works on this satellite is specialist in the composite. so he wanted to do the experiment. And these are the arguments. And for CubeSat, I don't see any reasons to use composite. Because for CubeSat, what matters most is the volume, not the mass. So by advantages gained by using composite is lost in a CubeSat. But if you are working on a 50 kilograms or larger, maybe using composite may have some advantages, saving masses.
Hi, thank you, Mr. Cho. Here. I have a question. I think in the last part of the presentation, he was talking about the low cost to send of launch attributes in satellites. So, when you say low cost, do you have which is the cost per kilogram launch?
Oh, yes. JAXA launch systems. They put those prices in the open domain, so you can check all this in Japanese. If we ask JAXA, 1U CubeSat, $30,000, $30,000 US. 2U CubeSat, 50,000, $50,000. And 3U, 880,000 US. If you ask JAXA, if you ask other company, it's about 3 times. That's so JAXA launch is really low because they are using Japanese taxpayers. So if the JAXA try to charge everything for their personnel fees and everything, I think it will become about 10 times.
Yes.
The only restriction like when you have primary missions, the launching that's positive. That's all.
Yes. Yes. So your missions must be suitable to the ISS orbit, and especially for 1U CubeSat, it can last. At the worst case, it can last only 3 months. So for education, it's okay. Actually, for the education, it's nice because we can see the end. But if you want to do really serious ones, yes, 3 months may be short. So you have to choose.
Bueno, buenos días. ¿Cuál es la perspectiva que se tiene a futuro cuál es su perspectiva que tiene de la ciencia espacial mexicana a futuro?
He's asking about your perspective of AEM. What's your perspective for the next exit?
It's very difficult. It's very good that the Mexico has finally space agencies. I knew those people from from Mexico long time in the UNICEF, and they are struggling to hold the agencies, but eventually it's home. So having agencies is now very good because the country can put the policy, put the policies and the strategies and work on. And how to implement is another issue. So also universities, there are several universities in Mexico, and working on a project, also doing some research. If you can consolidate and have some kind of network, and it may be also good. And one thing, there are many Mexican universities working on a small satellite, I see. And I like the word of the ESA former director, Jean-Jacques Dodans. He always said that the collaboration is slow, competition is fast.
Mm-hmm.
Right? And the one example is a moon race. The US and the Soviet competed to go to the moon, and they sent the humans to the moon in less than 10 years. Collaborations in ISS, it took longer than 20 years to build ISS by collaboration. Mm-hmm. So for universities, there are several universities, and they are competing. So I think it's good. So the nice balance of collaborations and competitions is, I think, it's really key. And for AEM, apps can coordinate that activities, and because AEM is kind of neutral for all the universities. That's my thinking.
Dorming. We are ham radio operators, so we have a small satellite. We have been working linear transponder for some time, and maybe 1 or 2 years we will have ready for go out to space. And what I am asking is a private funding, only for ham radio operators, but for general use. But I want to ask you if we want to access, if we have, if we can have your support for your institute for access to a low-cost launch.
Mm-hmm. Yes. Yes. You mean you want to launch amateur radio satellite?
Yes, of course.
I think we can help.
Yes, as ham radio operators, we have a very long story, more than 60 years of launching satellites to Earth. So Maybe this is the second hemorrhagia amateur satellite from Mexico. First was announced one, and we want to look for a low price launch. So is there a problem with that? Asking for you?
Yes, you can also ask Japan Amateur Radio League.
Yes.
Yes, they are also interested in this amateur satellite. They may be able to represent you. The Japanese amateur radio.
Okay.
They also have experience of launching.
Yes, yes, of course.
And also there are other company called Japan Manned Space Systems, JAMS. They are doing the business of the launch coordination using JAXA. And also we do, but as I said, we are not a private business. So we do because it merits our research and education. So if we can see the merit in a collaboration, yes, certainly. Thank you.
Okay, thank you very much.
Thank you. So, talking about the standard, so first part of the presentation. So for the perspective for the Europeans, so Spanish again pay us 9,100 dollars. So in that way, we want for this, which is the requirement. If
Yes, yes. In a big satellite project, the U.S. space company or the NASA, they don't use ISO. They use just NASA standard, their own standard. In Europe, they use something called ECSS, and JAXA use their own standard. So ISO is used only when there's some needs to do international collaboration or some international trade. This one, however, this is intended to serve as a guideline to people working on a small satellite in all over the world. Because those standards, like NASA standard or ECSS, we cannot apply for small satellite. If we apply that one to small satellite, it's no longer small. Yeah, it costs us too much. Costs too much money. So we are trying to make standard just good enough to the small satellite, considering its value, and so that can be used for the small satellite developers all over the world. Because right now they are not following any standard. And so they can be used, and also it can be used for the trading of the satellites or components. So that's what we see. So
let's not say that and this standard is not for launch just.
Well, to be launched to ISS, you have to follow another thing, the safety requirement. So that's a different from this one. For safety requirement, you have to do some testing. That's a very difficult. That's why if you want to launch through the JAXA, you need a Japanese partner because you have to coordinate with JAXA about the safety requirement. Kind of a unique requirement.
And thank you, Professor. Very, you have been very kind to us, AEM and Mexico, for you to share your knowledge. And be sure that we will be in contact with you. And we will be sending Mexican students. They are very talented students in Mexico.
Yeah, I know.
And we will work very closely with Kyushu. And I would like to ask Rodrigo to share some thoughts before we close. Just will share some experiences in Kyushu. Spanish for the sake of the audience. We will close the session. Afterwards, we will have tendremos una sesión de fotografía con todos y después podrán acercarse al profesor Cho. Nosotros tenemos que terminar aproximadamente 11:30, porque tenemos otra reunión después. Entonces, todavía hay tiempo. Vamos a pedir a Rodrigo que nos hable unos minutos sobre su experiencia en YouTube y tendremos la sesión fotográfica de grupal. Pues ya podrán acercarse al profesor Cho ya para que tratar de individual con él y a las 11:30 cerrando completamente. Por favor, Rodrigo.
Muchas gracias. Yo estoy estudiando actualmente doctorado en este programa QTech. También soy becado por el programa de Twin Stimulus. Apenas este mes cumplí el primer año y pues lo que les quiero transmitir es que en este primer año lo que ha sido mi curso de doctorado pues ha sido bastante enriquecedor. Un doctorado por lo general pues uno sigue su línea de investigación, pues hay una relación profesor-alumno para llevar a cabo este proyecto doctoral. En este programa es bastante especial. En primer lugar, pues yo tengo aunque tengo ya algunas tareas ya muy definidas, un proyecto ya muy específico, que es control de orientación, pues esta investigación pues sirve para alimentar a un proyecto. Ese proyecto es el que mencionó el profesor Cho, que es AWA del Oxford. Es un satélite, es un CubeSat de 2 unidades desarrollado en Singapur y en QTech. Entonces, pues al menos yo como partícipe de este desarrollo de este proyecto satelital, pues desde que me dijeron, bueno, el profesor me dijo, pues vamos a proponer este satélite, este proyecto satelital y esperemos la respuesta que tenemos. Pues para mí fue emocionante porque dije, bueno, voy a trabajar con base en un proyecto satelital y ya cuando nos dijeron, está aprobado y empiezan las juntas, empieza la relación más cercana con QTech y Singapur. Entonces, pues el hecho de participar en el desarrollo de un proyecto desde el inicio, desde el kick-off meeting, para empezar las juntas mensuales de cómo va el proceso de desarrollo, el preliminary design review, luego llegar hasta el punto, bueno, clinical design review y así, pues esa experiencia pues es bastante enriquecedora para uno que busca especializarse en lo que es en el campo espacial, particularmente desarrollo de satélites pequeños. Pero también la experiencia que he tenido ahí ha sido además el llevar cursos, los cuales son básicamente clases que se dan 2-3 veces a la semana, y pues uno ve de manera introductoria todo lo que es sistemas espaciales, satélites terrestres, pequeños, CubeSats, y todos los subsistemas en general. También por el objetivo de laboratorio, el cual es el profesor director, pues también vemos ambiente espacial, cómo es la interacción entre el satélite y el ambiente espacial en diferentes órbitas. Entonces uno ve en un panorama general todo lo que se trata, todo lo que vamos a enfrentar, o todo lo que uno enfrenta cuando lanza un satélite, es lo que debe considerar al menos. Ya en algo ya muy puntual, por ejemplo, la característica de cada alumno, de acuerdo a su línea de investigación, bueno, el profesor le sugiere qué materias uno debería llevar para pues, alimentar más el aprendizaje. Entonces, pero no solamente es eso, los cursos. También, al menos en nuestro laboratorio, tenemos una modalidad en el cual interactuamos con los estudiantes, que es el seminario de investigación, en el cual se hace cada semana y pues cada alumno expone sus avances en su investigación. Nosotros, como pues compañeros, amigos, basados en nuestra experiencia, en lo que hemos vivido, ya sea en esta escuela o anteriormente, pues les decimos, ¿sabes qué? Pues más bien haz considerar esto, haz considerar el otro, fíjate que deberías de hacer esto para esto. Es un aprendizaje en donde pues todos nos relacionamos no solamente como amigos también, y pues ya sea fuera del salón de clases también compartimos nuestras experiencias. Y además hay otra característica. Hay una clase en particular que se llama aprendizaje basado en proyecto, Project-Based Learning, en donde alumnos en equipos para desarrollar algún proyecto en particular. Por ejemplo, en el caso que comentó el profesor Chol, el BEARS Project, es un proyecto en donde son varios alumnos y desarrollan desde el principio a fin el satélite. Y pues para algunos de ellos, bueno, el país de procedencia, ese es su primer satélite. Entonces es bastante enriquecedor participar en todo el desarrollo del proyecto satelital. En el caso mío y el de otros, claro, en el cual no estamos en ese tipo de proyectos, pues en este caso nos pidieron hacer un equipo y participar en una competencia que se llama Mission Idea Contest. Entonces ahí es algo similar, en donde uno genera la idea y ya que se tiene la idea, se defiende. ¿Cómo se defiende? Pues a partir de todo lo que es System Engineering, Project Management, todo lo que uno debe de considerar para desarrollar el satélite y cumplir la misión. Entonces, por ejemplo, en nuestro caso formamos varios equipos y nos dividimos las tareas. Uno debe de llevar, por ejemplo, la carga útil, debe llevar estructura, lo que es análisis técnico, radiación, sistemas de potencia, etc. Entonces, tenemos que diseñar los sistemas, hacer simulaciones, por supuesto, para defender esa idea. Entonces, afortunadamente, la idea que nosotros generamos, pues, no finaliza esta competición y pues afortunadamente la vamos a defender, pero para poder proponer esa idea y defenderla, pues tuvimos que ver prácticamente todos los aspectos de un proyecto espacial, desde la parte técnica, la parte administrativa, cómo se va a implementar. Entonces, pues eso es otra manera de aprendizaje. Entonces, bueno, ya como conclusión, quiero comentarles que al menos en este primer año pues, ha sido pues, bastante, bueno, de hecho, excitante, no sé cómo decirlo, el hecho de que en un periodo de poco de tiempo, pues, haya aprendido tantas cosas y conocido gente. También es otra cosa importante. Todas las personas que uno va haciendo amigos cercanos, en ese momento, pues quizá en un futuro sirvan como contactos para futuras colaboraciones. Entonces, al menos desde mi punto de vista, pues yo si ustedes tienen ganas o quieren participar en QTech, estudiantes, o ya sea como una estancia corta de investigación, etcétera, de veras se lo recomiendo ampliamente. Y yo de mi parte, pues yo estaría pues complacido en ayudarles en lo que sea, ya sea consejos, lo que sea que ustedes necesiten, yo con mucho gusto. Muchas gracias.
Tengo una pregunta, perdón, para Rodrigo. Dadas, digamos, las posibilidades que tenías de opciones para hacerles, ¿qué te
bueno, en primer lugar, yo antes de llegar a Twitter, tenía, digamos, ciertos planes. Yo estaba trabajando en el Centro de Educación Espacial y sí estaba buscando, la verdad, oportunidades. Más sin embargo, no los estaba buscando tan enérgicamente porque yo ya tenía como que cierto plan definido y estaba considerando que tal vez en unos 3, 5 años después de establecerme como el Politécnico, pues iba a buscar un doctorado. Incluso aquí en México, de hecho estaba hablando con varios investigadores de la UNAM, para más o menos conocer todas las posibilidades y pues escoger la mejor opción dado a mi caso. De repente, pues, bueno, además de otras universidades que he estado buscando en Europa, surgió QTech. Y la verdad no lo conocía sino porque llegó un investigador, bueno, él no está ahí, pero salió. Y pues gracias a él, pues también igual, más o menos conocía a grandes rasgos qué es lo que hacía QT. Entonces dije, pues bueno, estoy interesado. Él fue el primer contacto que hice en QT. Entonces, él me dijo, ¿quieres hacer doctorado? Pues sí, la verdad es que sí. Entonces, pues afortunadamente yo seguí todo el proceso y pues después de unos 4 o 5 meses, pues después de entrevistas, someter documentos, afortunadamente, pues sí, fui. Entonces, el hecho de haber conocido gente en una primera instancia, pues sí, me motivó bastante para participar y afortunadamente estoy ahí.
¿Tiene alguna otra pregunta? Muy bien, pues muchas gracias, Rodrigo. Entonces, vamos a cerrar aquí. Antes de la foto, quisiera comentarles que actualmente la Agencia Espacial Mexicana tiene una convocatoria para un concurso de innovación espacial, aeroespacial, que lo está publicado en el portal educativo de la Agencia Espacial Mexicana, educacionespacial.am.gov.mx. Este es un concurso que estamos realizando de Boeing. Los invito a todos ustedes que están viendo vía internet a que revisen la convocatoria, ya que esta termina el 21 de octubre. Pero es la convocatoria se refiere a proyectos que hayan realizado ya. No van a realizar nada nuevo. Ustedes, un tesis de licenciatura, algún trabajo que hayan hecho, alguna práctica, incluso alguna idea, porque no es un desarrollo completo lo que tienen que hacer. Entonces, los invito a que revisen la convocatoria y participen en este. Bueno, con esto cerramos. Le vamos a dar un reconocimiento a los 8 recognition. Los 8. This is a recognition from the Mexican Space Agency. Y ahora sí, cerramos la transmisión y ahora sí ya podemos pasar aquí a la foto de grupo. Después de la foto de grupo, tendremos unos minutos. Si ustedes quieren interaccionar con mucho gusto.